Hello, welcome to discussion section 2, and I'm going to be explaining how to solve certain heuristic problems. Okay, so looking at question 1, we have a agent that's a car, and it can do actions go in 4 directions, or it can accelerate or decelerate, which is a fast or a slow action. So now we would like to see what its state representation is going to be like. Let's take a look at question A. So question A is asking for the size of the state space. We know that there is n by n possible positions that it can be. And then we also know that it can face 4 directions. We also know that it has a lot of possible speeds that it can be at. And what are they? They're 0 all the way to Vmax. So now that we have all this information, we can calculate the size of the state space. So how do we do this? We see all combinations of it, we multiply them together, and we will get 4 times mn times 1 plus Vmax. That's our solution to part A. Okay, moving on to part B. It's asking us to identify if a certain heuristic is admissible. So then what they want us to identify is the Manhattan distance. So is the Manhattan distance admissible? In some of our problems we saw that they were, but for example, Pacman search. But in this case it is actually not admissible, because of the situation where this agent, the car, can both accelerate and decelerate. For example, if we had a situation where we saw a long corridor with the agent 6 blocks away from the goal. We have the agent here, it is facing in this direction, and it wants to get to the goal. Assume that it had a velocity 4 right now. It can choose a few slow actions such that it gets to the goal in time. Now let's calculate how many it is. If we choose 1 slow action, it's going to end up here. It does another slow action, it's going to end up here. Takes another slow action, it ends up at the goal. And then takes a slow action, it ends up with velocity 0. So how many steps did that take? That only took 3, versus the Manhattan distance. The Manhattan distance was 6, which is not less than or equal to 3. So in this case, Manhattan distance is not admissible. Now, moving on, let's look at question 3. We want to identify now admissible heuristics that are non-trivial. So let's start with slightly easier ones. So obviously, because we have directions in this case, we have to at least be facing the goal. So one heuristic that is admissible is the number of turns the agent has to make before it faces the goal. So it will take at least that many actions to get to the goal. Now, let's make one that's slightly better than that. Let's see, for example, we had an issue with our previous heuristic, which was that it overestimated because it did not account for speed. So what can we do? We can directly account for it. We can have a d Manhattan distance divided by the maximum velocity, which will always be at least an underestimate of the true amount of time steps required to get to the goal. Okay, so now we can have a few more things that are better. For example, we can have some combination of how many turns it takes, and how many and the distance divided by Manhattan distance by the maximum velocity. But what if instead we also can take into consideration the deceleration? Then we're going to have a strictly better heuristic than either of the previous two. So this would be similar to the amount of time steps that it takes to deaccelerate to 0 is going to be Vmax time steps. How much is that? We have we will be at Vmax minus 1 plus Vmax minus 2 plus 1 distance away. I'm going to call this decelerate. And then the amount of speed, and we can assume that we're going to just go at max speed for the rest of the time. So how far we do that? We go at max speed. I'm going to call this dmax. This is going to be the Manhattan distance minus the deceleration distance. So then our heuristic then becomes we're going to keep it, we have a situation where if it's not far enough, then we're just going to keep it at d Manhattan distance divided by Vmax. And this is if the Manhattan distance is less than or equal to the deceleration distance. But if it is greater, then we can do the thing that we want, which is d Manhattan distance, dmax distance divided by Vmax, plus the amount of steps it takes to decelerate, which we know is Vmax steps. So we can see that the third heuristic here is strictly better than our first one, is the best, because it will always be greater than or equal to this one, which is better or equal than this one. So this we call dominating heuristics. Okay, now we're gonna go over some conceptual questions. Looking at part D, if we use an inadmissible heuristic in A-star graph search, would the search be complete? So we can think about that. If we had inadmissible and we're doing graph search, it will eventually hit all the nodes as long as the heuristic is not unbounded. So will it be complete? Yes, because it will eventually find a solution should it exist. However, now the question is, will it be optimal? And then an inadmissible heuristic will not guarantee optimality because it will make us think that a state that's very far away from the goal is actually very good and vice versa. So this is false. Okay, so now that we have explored an inadmissible heuristic, let's take a look at admissible heuristics. So now we're going to have the same question. If we have an admissible heuristic in A-star graph search, is it guaranteed to return an optimal solution? Let's think about that. So for admissible heuristics, all it guarantees is optimality on tree search. So for the part 1, admissible, this is no, because we're saying it's graph search, not tree search. So this implies that we need a stronger constraint on the heuristic, which is what we call consistent. So if it is consistent, then it will guarantee optimality on graph search. For the next part, this is more conceptual. We kind of hinted at the answer already. If you were using A-star tree search instead of A-star graph search, then the admissible heuristic will guarantee optimality based off of the definition. And it will a consistent heuristic guarantee optimality? It will indeed as well, because we have shown in class that a consistent heuristic is necessarily admissible. So consistent will also give us the optimal solution. Okay, so moving on to the last part, it asks us, is there a advantage ever to using a potentially inadmissible heuristic over having an admissible one? So now we need to think of why we would potentially want admissible heuristics. A-star attempts to use heuristics to decrease the number of nodes that it evaluates, so that will save us time. But there's two parts. It needs to both explore the node and compute the heuristic. A potential advantage of an inadmissible heuristic is that it might be really fast to compute. It might be super simple, single calculation, not super accurate, but it will give us a very fast computational time, which will save on the amount of extra nodes that it might possibly have to expand. So, Okay, so we're going to now look more into the conceptual aspect of heuristics. We now have a Pac-Man problem in an n by m grid, where we have at least 2 in both directions. And this is very much like Project 1. We need to eat all the pellets in the corners. So, looking at the first heuristic, H1, we have the maze distance to the nearest food pellet. Is it admissible or is it not admissible? We know that it has to go at least to the first food in order to eat all of them. So, it will always be an underestimate, and it is an admissible heuristic. Well, it is admissible. Now, looking at H2, it is the number of uneaten food pellets remaining. So, it will at least need to take the number of actions to eat all the corner pellets. So, is it admissible? It is admissible as well. Now let's look at H3. H3 is the sum of 2 admissible heuristics, H1 and H2, that we previously just saw. And this one, intuitively, it seems like it might be admissible, but it's actually not. Let's look at a counterexample. We had a 2x2 grid where we had pellets in each corner, and in our last corner, a little Pac-Man agent is here. Then, how many steps would it be to eat all the pellets? It would take 3 steps. But how many steps did the heuristic calculate? So H1, we can see that the nearest distance is 1. So let's see in our node. This is equal to 1 plus number of pellets left, which is 3. This actually gives us 4, which is not an underestimate to the true optimal. So this is not admissible. Now heuristic 4. We have a max between 2 admissible heuristics. Is this admissible? Now this has a little to do with the idea of maximum between 2 functions. If I have 2 functions that are both lower bounded by the true optimal, then there is no way, even if you were to choose the max, for it to be greater than the optimal value. So both of these, they're both underestimates to the true cost, so therefore it must be, even the maximum must be less. So it is admissible. Now we look at number 5, the heuristic 5. So it's taking the absolute value of the difference between the 2 of them. We see that both of them are positive, so subtracting the 2 can only make it smaller. So if both of them were already underestimates, doing this operation on it would only make it even more of an underestimate. So H5 is also admissible. Okay, moving on to part B. Now that we have identified which ones are admissible and which ones are inadmissible, we can try to see if we can make our only inadmissible heuristic, H3, admissible as well. So we need to find an epsilon. In our case over here, we said that we had 3 versus 4. It was not admissible. So we can just guess and check. We can set that epsilon equals 1. In fact, this value epsilon being 1 is sufficient as well. We can think of it this way. We have H3 is equal to H1 plus H2. So therefore, H prime is equal to H3 minus 1, which is equal to H1 plus H2 minus 1. Grouping them together, like so. This makes intuitive sense. H2 minus 1, we recall what H2 was. H2 was the number of pellets left to eat. So we want to eat 1 less pellet, and this one is the distance to the closest pellet. What this heuristic is saying to us is that we have to at least go to the closest pellet. We need that many actions. And then from then on, we need to eat at least this many actions to eat the rest. We are going to consider game tree problems. Game tree problems are usually when we have a scenario where we potentially are trying to maximize a utility that is different from our opponent. We are going to say that the maximizing nodes are you, and the minimizing nodes are your opponent. You want to maximize your own utility, your opponent might want to decrease that. So when we want to solve a game tree problem, what do? whenever it's a minimizing node, we choose the minimum of its children. And for the maximizing node, we choose the maximum of its children, in which this case it is 4. Moving on to part B, it asks us, which are the nodes that we can possibly prune? The answer is actually going to be the 15 and the 7. So let's take a look at why that possibly is true. So we are going from left to right in this tree. We first see 10A3, we choose the minimizing node, we see 3. So now we know in this maximizing node, we will have a value of at least 3. We will have 3 as our minimum. So when we come into the next node, we first see a 2, and then we go like, oh my god, if it's any greater than, even if it was a value that is greater than it in the next node, my minimizing node is going to choose the 2. But even if it were, and if it were less than, then at least I see that we have a 3, which is a best case scenario. So we don't even need to look at the rest of the nodes 15 and 7. We finish the rest of this. We just directly put 2 into this value, and then we are done for this subtree. We move on to the last subtree, which we first see a 6. 6 is greater than both 3 and 2. Nothing we can really prune from the next one. We see a 5. It's still not helping our situation. We see a 4. So in the subtree, we have nothing we can prune. Now, we look at a different scenario. Now all of a sudden, you're still one of the players, but this time your opponent acts randomly. So how do we represent that? We say that it is the average of its children nodes. Taking the average of 3 of its children, we get that this is equal to 7. We move over here. This is equal to 8. And then we go to the rightmost one. The average of these is 5. And then for us, we get to choose the maximum of them. So this is going to be 8. Now the next question is, can we prune any of these? And for expected max, whenever we have an expectation node or an average node, we actually cannot prune anything, because if we pruned it, then our average would have changed. So no, cannot prune anything. We now introduce this concept of an equalizer node, which tries to choose the value that is closer to 0. So let's just fill it out as described in the problem. Let's start with the bottommost layer. We go for our opponent. We said that this one would be -1. The one next to it, -3. Over here, -5. Over here, 2. We consider all the equalizer nodes. We choose the one that's closer to 0. This one's -1, closer to 0. Over here, closer to 0 is 2. And then we get to choose which one's the max. So we're choosing number 2. So looking at this tree here, if we do evaluate from the left of the tree to the right of the tree, what are the nodes that we can prune? Let's take a look carefully at it. So we go over here, we see that this is a -1. So we know that this is pretty close to 0. The next value that we see is a -3. So now we should realize something is up, because -3, if it's anything greater than that, this minimizing node is going to choose the value that's even less. But what if it were greater? But what if it were even less? Then it would be even further from 0. So no matter what, this minimizer node would not choose this value, so we can prune it. Now the question is, can we prune anything else along here? We see a -5, we see a 3, and then we would probably choose the -5 immediately, because we would be like, okay, we would see the -5, we want to choose it. This 3, we actually can't prune as well, even though this is the maximizing node and we saw a -1 here. What if potentially these two values are very, very negative? Then the equalizer node can still potentially choose this value, so we actually cannot prune it. Now let's look at a different scenario. we wish to fill in leaf values such that this pruning happens. So let's think about it. When would this value be pruned? This is the equalizer node, so the only case that it would be pruned is if this value was as close to 0 as it can be. So what would that scenario be if one of them were actually 0? So we set one of them to 0, one of them to be bigger than 0. I'm going to say that's 1. That way the minimizer node will choose 0. In this case, this equalizer node will definitely choose 0 because it's very close to 0. And then this whole subtree will get pruned. Now what will we fill in the rest of the subtree? We have to make sure that these values get filled in, or else it would have gotten pruned. Let's just put them all to be 1. In this case, because we have a maximizing node, we want to potentially see if there's anything better here. We'll fill them all with 1, so none of these others can be pruned. Let's do something similar here for this new subtree. Now we have both a minimizer and a maximizer in this order. So note that this is very similar to a regular minimax tree. We want to prune this last one, which implies that somewhere around here we will see a value that makes it not necessary to see this last subtree. So probably we're going to want to see something that is very close to 0. That way we know that if we have values here that are very big, then we know that the minimizer is going to definitely see 1. And then over here, as soon as it sees a 0, oh, let's not prune that one. We first put a 1, that way it doesn't prune this subtree. As soon as it sees a 0, then all of a sudden, this value is going to evaluate to 0. Once this value is evaluated to be 0, the minimizer node will choose something that is less than or equal to 0. But since we already saw a 1 in this scenario, this entire subtree will not need to be looked at.